So we're talking scientific method today. On its learning, you'll find a little thing that says quiz scientific method. We're going to do that, and we're going to see how far we can go. We've got a couple of little activities to do. We'll see how far we get with this. Okay, scientific method. I know it kind of sounds boring in a way because you learned about it probably in 7th and 8th grade, maybe before that even. It's kind of boring maybe the way that we teach it sometimes in school because it's like this very set rote process. But learning about the scientific method is really important in terms of just understanding how science works. If you understand the process of science, it becomes much more difficult to have the wool pulled over your eyes, to have somebody lie to you, to accept false information, because you not only question it, but you question it logically and thoroughly, right? It's a very different way of thinking. Science is a different way of thinking. And it's not that other ways of thinking are bad and wrong, but science helps us to achieve things in a different fashion. And it can be very, very powerful, as evidenced by things like people standing on the moon. Yes, we really did that. It really happened, right? As evidenced by the fact that we understand that our Earth is round and not flat. Or that we created this thing called the atomic bomb, right? Those are powerful things. That's science at work, right? So let's dive in and talk about what's behind the scientific method. So, turtles all the way down. What do we know? How do we know the universe is the way that it is? And how do we know that, right? What do we know about the universe and how do we know it? That's one of the biggest questions we're going to ask in this whole course. It's going to kind of be a defining question for us. Someday, recognize this, that the questions we're asking now that we don't really know the answers to sometimes, they might seem obvious to us. In much the same way as people now think, well, who in the heck in their right mind would think the Earth was flat? Right? Don't go on the internet because those people are everywhere. There's something wrong with people. But really, like some of the things we understand now, we might look back on generations from now, humans might look back on, and go, how in the world do people think that? It's so obvious to us. But it wasn't to our ancient predecessors. Okay? Now I put this photo up here because it illustrates a good point about something we're going to talk about later on, called the logical fallacy. And there's a story, I don't think it's apocryphal. Nobody's really sure exactly who it was that this happened to. It's kind of a famous story in science. But as it goes, the philosopher Bertrand Russell, which if you've ever read any Western philosophy, famous Western philosopher, it's kind of boring as heck in my opinion, but famous Western philosopher is giving a lecture, and he happens to be talking about astronomy, and he's discussing, how we know that the Earth is orbiting the sun, and that the sun is just a star that's along with many, many millions and billions of other stars that make up this bigger thing called a galaxy, and that we're in this galaxy, and our star, along with all these other stars, are orbiting about the central black hole in our galaxy. And he's explaining all this and saying all this and whatnot, and how we understand that the Earth is round and all these things. And this little old lady in the back of the room kind of stands up and says, well, that's all fine and good, but you've got it completely wrong. And Bertrand, kind of quirky old professor guy, looks at her and is like, what? She says, well, you got it totally wrong. The Earth is flat, and it's supported by the back of a turtle. And he looks at her kind of as you could imagine a professor might look at somebody doing that, like, what's wrong with you, crazy old lady? And he says to her, well, he's thinking to himself, I'll get her. He says, well, that's good, but what's that turtle standing on? And she says, well, you think you're pretty smart, don't you, young man? She said, but that turtle is not standing on top of another turtle, which is standing on top of another turtle, and its turtle is all the way down. And so it's kind of become a famous refrain in science, it kind of jokingly, but also true. This is a logical fallacy known as infinite regression, where when we point out that something that you're saying has nothing underpinning it, you keep saying, well, there's something else behind that, and there's something else behind that, to ad infinitum, right? So we'll talk more about logical fallacies as we go, but utilizing logic and utilizing logic properly is a key component of science. And being able to think that way and catch it and pick up on it when somebody's using one of these fallacies is powerful. And you'll start to get a feel for it, and you'll be able to do it a little bit. But it takes some practice. We'll talk more about logical fallacies, but you hear them all the time. They're utilized like crazy in commercials. Lawyers use them like mad, right? Politicians use them very freely. Right? Logical fallacies, which are false ways of reasoning, they're all over the place in our world. So it's good to be able to recognize them. Science helps us do that because it pretty much is the antithesis to that. So let's talk about some things that we accept in science. And this is one of the first questions on your paper there. You can jot this down. Lots of ways to phrase this. We hold some things kind of in science, and we want to make sure that we realize that we make these assumptions. So these are assumptions that we hold in science, and they're very important assumptions. But it's always important to recognize that you're making an assumption. This first one is called Occam's razor. Okay, and Occam, famous William of Occam, way back, I don't know when Occam was around. He was a monk, maybe Middle Ages, I don't know. This principle has been around for a long time. It's known as Occam's razor. And what he says here is that no more things should be presumed to exist than are absolutely necessary. In other words, the fewer assumptions an explanation of a phenomenon depends on, the better the explanation. Okay. And I summed this up down here, and we're going to use this later on. This is going to come back around, and you're going to see it at play. You'll see this thing work. When we're faced with two hypotheses that explain a particular phenomenon equally well, we should always accept the simpler of the two. So what do you do when multiple scientists arrive at different explanations of something in different ways, and they could be very, very similar explanations? You look at them and you go, which one is simpler? And you accept that one over the other one. Now why do we do that? Because, first of all, as Occam said, you don't want to make up more stuff than you absolutely have to make up to explain something, right? And secondly, in everything we've learned about nature, almost always the simplest explanation for something is the truth. So we utilize this quite a bit in science. We'll use Occam's razor to cut the garbage right on out. Everybody have it? Any questions on that one? It's pretty easy. You can follow right along. You can type in your Word document that I know you hate. Okay. The next one is called the Cosmological Principle. This is a big assumption that we make. It's hard to find jokes about science. It really, truly is. So this guy is sitting here on the couch, and his girlfriend says, "Does this skirt make my butt conform to the cosmological principle?" And he says, "Why, yes, your derriere looks great from every angle in the universe." So it's mildly humorous if you understand what what the cosmological principle is. This is an assumption that we make about the universe. And it says that on large scales, the universe is the same everywhere and in every direction. There's a lot that goes along with this. In one respect, it's saying that if I look one direction in the universe, there's not necessarily a preferred direction. Okay? There's not more galaxies in one direction than there are in another direction on a large scale. It's also saying that the physical laws that operate in our local area, in space here, operate the same everywhere else. In other words, gravity, the laws that govern quantum mechanics, all the laws of physics, they operate the same everywhere in the universe. Now, on one hand, you can look at that and go, well, duh, right? But on the other hand, you have to accept that we're making an assumption that that's the case. But recognize that if we didn't make this assumption, there would be no point in doing anything. We might as well give up and go home. Because if things can behave differently in different areas of the regions of the universe, then whatever theories and laws we devise here are worthless. Right? They're not really describing reality. But there's very good reason for believing that this is true. There's a lot of really good reasons. For instance, what if we had this hypothesis that said something along the lines of, in the Andromeda galaxy, which is our nearby galaxy that we're going to eventually collide with, which is very far away, by the way, the matter there is kind of reversed in polarity. In other words, the centers of the atoms, the nucleus, is negative, and the cloud of electrons on the outside of it is positive, right? Well, you better have some pretty good proof if you're going to make a statement that is as bold as that, right? So it's not that we couldn't make that hypothesis. Sure, we could, because we could falsify it, we could test it, but you would need to kind of explain a lot of things that we don't see. For instance, where's the boundary between this weirdo matter and then the regular matter that we're talking about over here? And why isn't everything just being destroyed and annihilated at said boundary? Like, we ought to see some flashy lights there, because matter that's differently charged is going to cause some very different situations. So we have to accept that, like, everything, gravity, quantum physics, is the same everywhere in the universe. Now, that's not to say that there's not local differences with some things, right? And it's also not to say that you won't have a different gravitational little g number if you're on a different planet, right? So, like, if I feel the force of gravity here differently than I would on the moon, because the moon is much smaller in mass, right? But we understand that in terms of our theories and our math, right? It's not actually behaving differently. Okay, kind of makes sense. Cosmological principle. It's a big assumption we make, and certainly you can question it, but you better have some pretty good evidence, because everything we've seen so far shows that this is the case. Cool. So what is science? Science is a method for learning about nature. At heart, that's what we're trying to do. And the scientific method roughly works like this. And you're welcome to jot this down for your scientific method if you like. I'll put a bigger slide up with what that really is. You get an idea. You have an idea about something. You ask some questions about it. You notice some things. And then you create a hypothesis about that. If such and such is the case, then such and such should happen. Right? You make this prediction. And then you test that prediction. You see if you can prove that prediction wrong. That's pretty close to pretty much how it behaves. Now, the other day when we did that, we had our discussion in class. You guys had some great things to say. You did really good on the questions. One thing that kind of kept coming up as being a little bit confused, or if it wasn't confused, it was just hard for you to explain, which I get. Some of this stuff is hard. A hypothesis always has to be falsifiable. And it's confusing because it sounds like I'm saying it's false. It's not false. What we're saying is that there has to be a way to test it to see if it is false. Not a way to test it to see if it is true, because you never truly prove something 100% true. But there has to be a way that you could show that it could possibly not work. And if you fail to prove that it's wrong, then you start to accept it. Kind of hopefully, maybe the more times I say it, the more it'll sink in. Okay, everybody got that one good? Trying to see what is on the quiz. There you go. So let's talk about provisionality. Every bit of scientific knowledge is provisional, and you guys nailed this the other day during our discussion. You brought this point up, that scientific knowledge is provisional. So scientific theories and laws have to be capable of being falsified. Okay? There has to be the potential that they could be falsified and rejected. And really, that's how science moves forward. In some respects, people might think of this as a vulnerability to science, but really it's its greatest strength. The fact that science, all science, is malleable. Every single thing in science could be changed. Now, that's not to say they're going to be changed, because it could be really, really difficult to change something. Like our theory of plate tectonics, you better have some really, really smoking good evidence if you're going to attack the theory of plate tectonics. Why? Because every single experiment that has ever been done has confirmed it. Nothing has falsified it for a very, very long time, and people have tried. Einstein's theories of relativity, you better have some really good evidence if you're going to go after that one, right? But in the end, all it takes is one piece of really solid, good evidence to rock the whole boat, to turn a theory on its head. Right? So that's why we sometimes we hear people saying, well, you know, just how strong is the theory of evolution? You know, is it really a strong theory? Well, people have tried and tried and tried to to prove it wrong, right? Over and over and over and over and over, and everybody's failed. Like not a single scrap of evidence proves it wrong. How could you prove the theory of evolution wrong? Oh heck, find a fossilized dinosaur anywhere in a Cenozoic layer. Okay? Find a fossilized rabbit in the Paleozoic. Ain't never happened. But it would be that simple. One simple bone and the whole thing we'd have some serious problems. But it's not ever happened. It's not going to happen, right? So it's really a strength of science. Everything is subject to change. It's malleable, okay? And that's good. Like I said, even ideas that are as powerful as Einstein's ideas that have been accepted as truth for like 200 years, we still scrutinize them. You will still see studies come out questioning some of Einstein's results or trying to put forth a different hypothesis as to how things work. Was Einstein's theories the final word on the subject? Almost certainly not. There's something bigger and more grander than that. I guarantee you. I'd be shocked if there wasn't. Right? But more than likely we'll be tweaking it, not just throwing the whole thing out. Okay? In terms of Newton that we talked about last time, like Einstein's theories, even though we still use Newton's theories, replaced a lot of that. Right? They changed that. So in the end though, and this is one of the questions on your paper, every theory that we have, every law that we have, gets tested against nature. We see if nature can prove it wrong. And then we know whether or not we have to change it. Okay, so that's where everything's being tested. If we wanted to kind of show what science is after here, I think this picture really sums it up. In science, what we try to do, what scientists try to do, is to discover patterns. And I would argue that scientists are really just better at examining the world than the rest of us. Like they notice things that many people miss. And they ask questions about those things. The things that they notice are patterns maybe that everybody else has taken for granted. Like in this picture here, the seasons. The seasons are definitively a pattern. They keep occurring at the same times throughout the year and repeating. For how long did people go on seeing this pattern? Like they knew it, right? Like ancient peoples knew this pattern. Nobody questioned why. Like, can we probe this? Can we discover why this pattern exists? Right? Scientists figured out why this pattern happens, right? It has to do with the axial tilt at 23.5 degrees of the Earth and the fact that we go around the sun. And because of this tilt, at different times of our year, our cycle around the sun, a different part of the Earth is tipped towards or away from the sun, the different hemisphere, which gives us our seasons at exactly the same times every year because it takes a certain amount of time to go around the sun. And so we understand that now because we deciphered this pattern. And remember, they deciphered this pattern way before we had satellites. So science was able to discover this. Do you need science if you can just look at it? You wouldn't need science to discover the seasons if you had a satellite in space, because you just look at it, right? You wouldn't need science to tell you that the Earth is round if you had a satellite in space, even though some people still won't believe that. Because you just look at it. Science is for discovering things you can't see, things you can't experience, for probing the unknown, right? So sometimes it confuses people because they're like, well, yeah, we already know that. Well, yeah, you know that now because science showed it to you, and then our technology developed to the point where you can just take a picture of it. Right? So it's confusing sometimes. And we said here, math is the language of science. We're going to use some math today. Math is the language of science because it's the language of patterns. It's how we describe patterns. That's really the purpose of math. Don't tell a math teacher I said that. Probably people think math exists for math alone. So math is just there so we can use it for science. That's the only reason. So this helps us make predictions, right? Okay. So I want to show you here, this is kind of a schematic of sort of the scientific method. And this is what you might see in a textbook. Like you define a problem, you form a hypothesis, you make some observations, you test the hypothesis, perform some experiments, you collect your data, you ask yourself, do the experiments support my hypothesis? If they do, you go, yay! If they don't, you hang your head in shame. And you question again, like, how can I maybe redo this, rework this, right? Eventually, if you come out with some things that really are seeming to support what your hypothesis was, you would then communicate the results. Probably the most important part of this picture up here is that you communicate your results, right? Science is changeable, and we require other people to look at our work before we accept it, okay? Now, does science really involve this nice, neat pattern of discovery like this? No. No, it doesn't. It's way more messy than that. We'll talk about that here in a second. I want to give you an example of how you use scientific reasoning. You guys all do this. You maybe don't follow this exact pattern, but I guarantee you think logically about problems, and you don't even recognize you're doing it. The trick is to recognize when you're being illogical. So here's my baby ginkgo trees. So you guys don't know this about me. I'm sure you already think I'm pretty weird, but I like ginkgo trees. I think ginkgo trees are awesome. I think my favorite tree, if I could have a favorite tree, I guess I have a favorite tree, it's a ginkgo tree. They're ancient. They're like, you walk underneath some ginkgo trees and it feels like you're in the land before time. You're like looking around for where the velociraptor is going to stick its head out. Like they're ancient trees going back into the fossil record. In the fall, when their leaves change, they change this brilliantly gold, like yellow color. And they're so striking and noticeable. I guarantee you've seen them on the streets. They plant them, they're usually fairly small. In cities, oftentimes, what you may not know is that the only type of a ginkgo tree they'll plant is a male ginkgo. They will not plant a female ginkgo because there's two differences. And some trees have both parts, male and female parts, but the ginkgo is ancient and there's a male tree and a separate female tree. Now, the female trees, when they grow up, they produce this fruit. And it's about maybe 2 inches or so-ish fruit. And there's a seed inside, and then there's this fruity covering on the outside. And when those things fall, they smell so god-awful, I can't even describe it. It is such a bad smell. Like, the smell is kind of like, I think it smells like hot vomit. It's just like foul. Has anybody ever seen these female ginkgo trees? There's a few around town. They're not many, though, because people will cut them down because they smell so bad. Yeah, if you end up going to IU or ever spend some time on campus, on the far west side of campus by the Sample Gates, there is a small grove of like 3 gigantic female ginkgo trees. And once a year, these things drop fruit. And I can't help myself. I have to walk. They're just so beautiful. I got to walk under them, you know. But then you're sitting in class and you're like, what's that smell? Oh my, who threw up? That's just terrible. It's so foul. You would not want to leave these things in the back of your car, maybe your enemy's car on a hot day. It would be something else, let me tell you what. But anyway, one day I decided to collect a bunch of these, and of course I walked around with a sack of these ginkgo seeds all over the place. I'm sure people in my classes were just like, oh my God, what's wrong with this guy? Smells so bad, right? Anyway, I took them home, and I planted them all in a big pot, not single and solitary like this, and I let them start to grow. And as my ginkgos grew, I was watching them, you know, because I was obsessing with my little ginkgo trees. I made some observations. I didn't sit down myself one day and go, hey, Hambling, it's time to make some observations. I just walked by my ginkgo plants, and I was like, oh, check that out. Look at those things growing. And I noticed that the ginkgos had the same growing conditions, but they were different sizes. Like some of them were really tall, some of them were really short. Some of them hadn't sprouted at all, right? And then they'd suddenly start to sprout like in a couple of weeks. Like they were very far apart. So that's really weird, you know? And thinking back on it, you know, like things like cornfields they're all the same height. It all grows up at the same time, and then we harvest it, whatnot. And I started asking kind of some questions about that. I wonder why that is. I didn't sit down and go, now it's time to formally ask a question about the ginkgo trees. I was just kind of thinking about it, you know? And I thought to myself, you know, why do different plants of the same species grow at different rates? That seems like a strange thing. So I thought, you know, if I was going to make a hypothesis out of this, I'd wanted to find some variables like which things are going to be changing and which things could I control if I really did want to do an experiment. Well, I kind of did an experiment because just the way I planted them all in the same soil, they got the same light, the same air, the same nutrients. They got everything the same, but they were all growing at different heights. It's like, well, how could that be? And like I didn't like sit down and think this all out like this, but it was just some thoughts that rambled through my head really quick. Like, well, maybe there could be genetic differences. There's got to be. Because like every other kind of variable is really kind of controlled here. There's got to be something genetic going on. And I thought, well, what would be the purpose of that, right? Well, maybe it's a survival trait. Maybe sprouting at different times means you survive. What if a bunch of ginkgo seeds fall on the ground and they all grow at the same time and a forest fire wipes them all out? There's no babies left. Right? But if a few of them wait, because of genetically this programming is different, they kind of pop up at different times, you've got like a built-in survival mechanism there. And I don't know how you test that. There's probably a way. I mean, somebody probably knows the answer to it. But I was just glancing at my baby ginkgo trees and enjoying them. I still don't know which ones are males and females. They're still growing. I planted them on my hillside. I have my own little ginkgo forest, right? But maybe there'd be a way you could test that hypothesis. I don't know. I'm sure the answer's probably out there. Surely somebody's thought of this. But I just thought it was kind of neat, right? And you draw some conclusions and publish your results and see what people think. The point is, real science doesn't necessarily work like the scientific method. Real science is kind of messy. Scientists don't just walk into work in the morning and go, all right, guys, kind of huddle around here, huddle around. We're going to make some observations today. Who's got an observation? Okay, let's ask a question about that observation. And now let's see if we can formulate a hypothesis that we can test. Is it falsifiable? And then they kind of go on about their little piddly work and see if they can falsify it, and then come back and go, it's time to discuss our conclusions. Right? It doesn't work that way, not in any setting that I've ever been in where scientists have been working. Scientists are working on some idea they've got and trying to come up with a way to build some apparatus to test this idea, and they happen to walk into somebody else's lab and notice something going on that maybe nobody's even looked at before, and suddenly an idea sparks, and they go back and they kind of piddle around with it and take some good notes on it and think about it a little bit. Right? But in the end, they end up kind of formalizing it like the scientific method. But it doesn't necessarily work that way. It's way more messy than that. So kind of the way we teach you in textbooks isn't necessarily the way it always plays out. Scientists don't do that. They're like you and the rest of us. Now, the point of it is that the heart of science, really, if you ask me, the heart of the scientific method, all of it, is asking questions. Asking good questions. Because in science, sometimes there's questions that are not as good as other questions. I know you've been told all along that every question is a good question, but not so much, right? There are questions that science can't approach. There's questions that are not phrased very well. We want questions that we can test, that we can dig into. So asking good questions, that's one of the main things at the heart of the scientific method itself, in all science. Asking those good questions. All right, let's move on to talking about the difference between a theory and a law. It's one of the questions on your paper there. So the heart of science is asking good questions. We touched on this the other day. We did a really good job of touching on this. I don't even know if I really need to say it, but what I want you to recognize for your questions there is that theories and laws are on the same footing. One isn't better than the other. It doesn't go hypothesis, theory, law. It goes hypothesis, theory, and law. Like they're on the same level, okay? So the difference is that a theory is, both of these are well substantiated. There's loads of evidence backing both of these up. Has to be, or they wouldn't be there. But a theory is an explanation of kind of how something works. It's a description of a broad process, like plate tectonics, a big, huge description of how this thing works. Quantum mechanics, evolution, it's a big description of how something works. Whereas laws are way more specific. Laws are specific to certain circumstances. For instance, we talked how Newton's laws of motion only work at sublight speeds. You got to be moving slow to use Newton's laws. If you start moving faster, they don't work. And yeah, it's a real thing, to the point where we couldn't use Newton's laws to understand the satellites that are going around our Earth. We've got to use some of Einstein's work to do that, because relativity comes into play. Time dilation, weird stuff like that starts to happen. And if we didn't account for it, all of our cell phones would be screwed up. So believe it or not, we're using that stuff right now. Okay, so laws tend to be much more specific. Okay, certain circumstances. There can be a law and a theory about the same thing. okay? And scientists are the worst about confusing these things because usually we just call it whatever sounds good. If it sounds funny to say, we say the other thing. But in the end, it doesn't really matter because they're really on the same footing. But I just don't want anybody to think that, well, you know, someday the Big Bang Theory will be replaced by the Big Bang Law. Because it ain't going to happen. Because the Big Bang is a description of how the universe formed. Any description of how the universe formed is going to be a theory. But if there's a specific description of how math operates in some various circumstances, then that will probably be called the law. Okay? That's what we're talking about. Okay, everybody got that one? All right, let's talk a little bit about theories and kind of how they're models. Science is really about making models of the world. Not just the Earth, but the entire universe is what we're trying to make a model of. And I just wanted to take a second to kind of reiterate that every model that we make really has to be something not only that can be tested, but also let's recognize that all of our models, our theories, our laws, they're all provisional. Okay? In other words, there's no way for us to make a model that's the real thing. We can't make something that big. We can make a model of the Earth that's a flat sheet of paper that we call a map. Okay? It's very useful sometimes. We could make it even more correct by making a globe like we said the other day. Looks a little bit more accurate. But to make the real thing, we'd need the whole Earth. So in some respects, like we're always making every theory, every law is really an approximation towards truth. Okay? In a way. That doesn't mean that they don't work and they aren't true. It just means everything that we do in science is really an approximation. That's why they can always be changeable. Because we're always trying to make it better than the last one to see if we can test it again. Okay? And that's really a strength of science. It shouldn't be seen as a weakness. Those theories, they're always evolving. Got it? Pretty good. So I think that's most of the questions on there. Anyway, I was thinking about this stuff, and I was thinking about, you know, creating a hypothesis and testing it, and really just how it's tedious and it's hard. It's just a lot of work to do science. And I think a lot of people don't recognize just how much work, how much tedious work it is to really do science. We cut through all of the like hard stuff in here because we're after the big understanding. We want to understand things. But to be a scientist is to collect reams and reams of data and carefully sift through it and try and tease out the patterns to understand why and how and come up with innovative ways of looking at things. Like doing real science is very much a lot of work. And a lot of people, I think, have gone into school. I've heard it from folks before say, you know, I wanted to go into school to do science. I wanted to be a scientist. And as they get further into it, they realize, my gosh, this is really hard. This is a lot of tedious bookkeeping and work and tracking and careful observations and keeping track of everything. It wasn't just sitting down, coming up with a big idea and being like, look, I did it. Right? It's hard. So when I was thinking about that, I was thinking about how I've had sort of an ongoing experiment that I've been doing for, oh my goodness, most of my life, I would say. And I thought I would tell you about it because it's also the time in my life that, one of the times in my life that I was pretty certain that I wasn't going to make it. It's kind of an interesting story, so I thought I'd share it with you. But anyway, for most of my life, I've been studying wood, trees. Because as I grew up wanting to live in the woods and spend more time in the wilderness, I wanted to know which types of trees worked the best for making fires. I don't mean just like lighting the fire. I mean like actually rubbing stick on stick to see if I could make a friction fire. Okay? And so at one point in time, I don't know how long ago, I started taking notes on this process. Okay? And that kind of evolved into me collecting bits and pieces of sticks and twigs from everywhere in the world from trees, from cacti to like about any plant you could imagine I have in my basement. So yeah, if you didn't think that Hamling was weird, yeah, dude's a little weird. Okay, I have boxes and boxes of very carefully carved sticks in my basement, among other weird things that you would probably think that I'm strange for having. And yes, they're all dated and labeled and everything else. Very tedious stuff, if you will. And so for years and years, I've kept track of all this stuff. And every so often, I get my box of sticks out, and I work on it a little bit, and I take some new notes, and I put them down in my spreadsheet. And I printed this off a few years back. It's quite a bit larger now. This was just the top few lines of my spreadsheet on the data that I was collecting. It goes like this. So this is like the A tree species through like starting the beginning of the B tree species, and it goes down. It's really long. It's kind of big. I can't even hold it all the way out in my arms. So, yeah, like what kind of stuff is on here? Well, a lot of stuff. Everything from, there's even more on there. This is really old. I've got scientific name, family, obviously. Characteristics, grain, texture, density, mechanical strength. What's its specific gravity when it's green, air dry, oven dry, green, air dry? Its bending strength. What's its stiffness and bending? What's its compression parallel to the grain, perpendicular to the grain? What's its maximum workload? What's its hardness? What's its shear strength parallel to the grain? How much does it shrink when it's dried in an oven versus air dried versus allowed to dry with 12% moisture? What are its working properties? Is it hard or easy to carve? How decay resistant is it? Is it permeable or does it repel water? What's the structure of the wood? Does it create striations when I make a fire? Does it have a thick cambium layer that's useful for making cordage? And then other notes. Like that's just one column going across, right? So it's a tremendous amount of data. But when I started thinking about it and thinking about science, and honestly, I wasn't sitting at home going, I need to do an experiment. I was like, I really want to know the answer to this question. I had a question like, what makes it good for bow drills? Because some trees work really, really well. Some trees don't work at all. And it seemed kind of weird to me. So I started trying to control for factors. And I found how difficult it was to control for different things. Like, I wanted to make sure that I always harvested from the same part of the tree. I didn't realize that early on, but there's differences. Is it a root? Is it a stem? Is it a trunk? Is it branch? I wanted to get the same age trees. I wanted to let them dry the same amount of time. I wanted to make sure that they were the same amount of rottenness. Like, there were so many factors involved like that I had to control for. At some point I recognized, I was like, oh my gosh, like for a scientist trying to tease out the mysteries of the universe, how difficult. Like how difficult. Like I'm just looking at different trees. Like how hard is that when you're talking about stuff you can't even see, right? So I thought that was kind of interesting. But anyway, I put this in here just as a photo, so I thought I'd kind of explain it. So this is my cousin Serge, and Serge is a Canadian. Of course he is, right? You guys know that my family's Canadian. I just found out the other day that I'm actually have dual citizenship. I took a quiz online on the Canadian website, and they said I have dual citizenship. How about that? So part Canadian. Anyway, yeah, I could move to Canada and get a job. How about that? So anyway, once a year I go up to Canada to visit my family up there, and they live in northern Quebec, way up far up north. They all speak French, so I don't understand them, and they don't understand me, but somehow we manage. And along with eating some poutine and the usual things you do in northern Canada, we play the family reunion hockey game. So we all get together and we get on the ice, and actually, real deal. My family is the only family that has enough hockey players on it that our team is just our family. Every other team comes from different parts of the area, like from the Indian reservation, from like all over the place. Different teams come to play in this huge tournament, but my team is just a family team. And so it's made up of like various like young people, mostly like a lot older people. Like we're not typically the best team on the ice because we don't even practice together, but we play like one game a year. Anyway, just to give you an idea of how tough my cousin Serge is, this guy played semi-professional hockey for a long time. A lot of my family members did. And he was on the teams that, well, if you've ever seen the movie Slapshot, like that was made off of his league. So he was like the guy that they would say, Serge, number 23. And Serge would go out on the ice, and Serge would just pretty much murder the guy. And then he'd get back in the box, right? Like, he was the thug. He was the guy that they just sent out there. His team paid for him to have boxing lessons. Like, that's how he trained. That was the kind of hockey he was playing. It was not the kind of hockey that they would play down here in the States. Anyway, big guy. Look at the size of that guy's hands, right? Like, you could fit like 3 of me inside of him. Are those what? Those are his gloves, actually. He's warming his hands up. But anyway, they look like squirrels, don't they? Anyway, this fire right here was made with nothing but 2 sticks, friction fire. So I'm up there with my cousin Serge, and we're trying to communicate. Can't really talk to him very well because he speaks no English. And he found out that I really loved the wilderness, and I spent a lot of time out there. And he said, well, we should go out in the bush, roughly the translation of what he was saying. And I was like, yeah, that'd be great. He's like, well, let's go tonight. I was like, okay. He says, well, he's like, what do you want to bring? I was like, well, we can just go out there for the night, if you want. It's middle of winter in Quebec. It's freezing cold, right? And he's like, looks at me, he says, well, you want to bring some food? I was like, no. I said, we'll be fine, He says, well, I'll be okay. And he's like, slaps on his big tummy. He says, but I don't know about you, because I'm apparently not the biggest of guys. Anyway, he says, if I get hungry, I just eat you. I was like, are you serious? You being serious, Serge? I don't know. Anyway, yeah, we walk out on the coldest of winter nights in northern Quebec, and we're hiking into the bush, and we cross this frozen lake. He lives way out in the middle of nowhere, too. And get to the other side of this lake, and we kind of find a spot for a shelter, and we build this shelter, and sticks and leaves, that sort of thing, and dig down to the snow a little bit to the bare ground, and we're kind of setting up a place for the night. And he kind of communicates to me that he's going to go find a beaver. And like, you're going to go get a beaver? Like, I don't even want to question it. Like, he's just going to go catch a beaver. I don't know. So he just kind of takes off, like, just leaves. And like, we're going to die. We're going to die if we don't make a fire. Like it's unbelievably cold. It is so cold up here. And so I wander off into the woods, and I'm standing in this snowdrift. I'm like up to my waist, and it's really deep snow, and I've collected this stick. And like I just told you, like, is you be very, very particular about what sticks you pick up. If you watch it on TV, sure, it looks like people rub sticks together and poof, a magical fire appears. But it really ain't that easy. Like, it takes time. At my best in wilderness conditions, if I need to collect all the materials, it might take me about an hour. And that's like at my best. Like, if I have to collect everything and carve it from scratch, if I've got a knife. If I'm using stone tools, it's going to be a whole lot longer than that, right? And a whole million things could go wrong in the meantime. So I'm standing there in the snow, and I've got this twig. It's like as long as my arm that I'm carving for a bow. I'm making, and I've got some other sticks poking out of my pockets, and things are drying in various places on me, trying to get them as dry as I can. I'm carving along on my stick. I'm standing in the snow up to my waist, and I look out across the lake, and I see this speck out there, like in the far distance, this little dot, the black dot. I'm like, thing's moving out there. I'm like kind of carving my stick, and I'm watching it. Like, partway across the lake, I see it kind of turn and start heading towards me. And as it gets closer and closer, I suddenly realize that it's a wolf. Like, it's an honest-to-God wolf. And I've seen wolves before at the zoo. Like, I never seen a wolf in the wild. Do you know what? That those wolves at the zoo, that's a lie. They're not really that size. They're 3 times that big. They make them like, I don't know, they miniaturize them at the zoo. Because in real life, they're like 3 times that size. They're bigger than any dog you've ever seen in your life. They're humongous. And when you're standing in a snowdrift up to your waist, they look even bigger. And this wolf just comes trotting like full speed at a sprint off of this lake, up the snow, and stops like not 10 feet from me. Like literally like the back of the room here where you're sitting. Like that's where it's standing. And it just stops, and it's staring at me with its beady eyes. And it is humongous. And I'm standing there, and I've got a stick in one hand. It's like a little twig. And I've got a knife in the other hand, which is all of 3 inches long. And I'm standing there, I'm thinking to myself, this is it. This is how Hambling dies. This is the end. It's all over for me. Like, I'm at least going to poke this thing once or twice before I'm eaten and drug off to pieces. Because what am I going to do? Start shouting for my cousin who's out catching beaver? Like, what am I going to do? There's going to be a big blood spot on the snow. Like, that's going to be it. But luckily, it just very slowly starts to circle around me, just watching me the whole time, and I'm just kind of turning with it, like here, any minute we're gonna go. Like, this wolf and I are just gonna go, and luckily it just runs off into the bush. But I tried to explain this to my cousin, and I think he just thought like I saw a wolf in the distance, or like I was just being goofy or something. I don't know. I don't think he really ever understood it. But he's sitting there at a fire that I almost died to make. But yeah, we got a fire going. It was fantastic. Super nice to be warmed by a fire. He didn't catch a beaver. All that time he was out just playing somewhere. I don't know what he was doing.
So you're telling me you have family that you go visit often, only speaks French. You know all this stuff, and you have never taken the time to learn French.
Well, okay, let me explain that. I took French in high school because you have to take a foreign language, right? Because I thought, oh, it'd be good because I can speak to my family. Well, they don't speak French like you learn in high school. Yeah, it's more like Bayou Hillbilly French. It's like when I say words to them, they don't understand what I'm saying in French. Yep.
And then there was Canadian French. And they had like different meanings for like different words that
Really?
yeah.
I didn't know they taught that. But you know, the French Canadians settled down at the bayou. So when you think about how people talk down there, that's kind of like a similar type of a situation. Yeah. Well, to give you an example, Gracie, I tried to ask one of my younger cousins if she was hungry, and she ran away crying from me, and it was a huge ordeal. And I was like, I don't know what just happened. Went in the house. Apparently, I had asked her if she was a woman. She was pretty upset with me, and there was no way for me to apologize. I couldn't. Like, they just didn't understand what I was saying. It was pretty funny though. Yeah. No, this was before Google. But yeah, everybody, if I still go up there today, they'll still laugh about that story because it was pretty funny. Yeah, why not? I traveled all the way throughout Mexico. I don't speak any Spanish. I just write stuff down and hand people things that I wrote down and say, what bus, what bus? Hopefully get on the right bus. I had a compass. I could figure it out eventually. Oh, it's fun.
My grandpa is like full-blown like Native American, and his name's Geronimo, and he lives out in the woods in like eastern Kentucky, and he pays no taxes, and he built his own house.
Oh, that's neat.
And he lives out by fishing and hunting, and we're like, how does he get money to like for medicine and food and stuff? Because he doesn't go to the grocery store. He goes like once a month, and
Really? That's cool.
like every time I go down there, he's like,
That's great. You should go learn some stuff from him.
no.
The crazy people are the interesting ones. That's how it works. Anyway, really, like, you got to think that the variables are the factors that you're either controlling or manipulating an experiment, right? And some of them you've got to control, and you've got to pick one that you want to change, right? And then there's one that you're going to look at the results of. But really, it takes a lot of time in science to identify all the variables that are going to influence your experiment. And a lot of experiments that get run, somebody else will look at and go, you didn't control for this. Like, here's a situation that could have affected what you did. And that's why one of the things that's important is that we share our information, right? So I'll leave you with one last little bit of quantum weirdness. And that's that in the end, it might be impossible to be truly objective. In science, we always really try to be objective. Like, that's the goal, is to be completely objective about all of your work. But what we've been finding in terms of our understanding of the quantum realm is that even just observing an experiment can cause the results to change at the quantum level. So there's a lot of stuff that we need to explain and understand, but by and large, like, we really try to be objective. Science is about objectivity. It's not about being subjective. And that's why sharing your work is important, because somebody else can pick up on your biases and on your things. Because believe me, even scientists have biases, right? They have personal beliefs and thoughts and things that can color how they do their work. But if we share that work, other people will notice. And that's what's important, and that's how science works out. That's Serge blowing on a piece of tinder fungus that I lit on fire. It's pretty cool, huh? Yep. In the morning, you know what? We woke up in the morning. I tell you this, it was so cold. Fire went out, of course, right? In the morning, we woke up, and I'm freezing. Like, I'm seriously like worried I'm gonna die. So I try to start another fire, but after 3 attempts, my hands are so cold I can't feel them enough to actually hold anything. Like that's cold when you can't actually move them enough to do anything. And so I'm doing the dance, like, dancing around, trying to stay warm, trying to get Serge up. And Serge finally gets Serge up, and he goes to put his boots on. Well, he didn't take his boots to bed with him. If you've ever winter camped before, like really winter camp, not in Indiana, you got to sleep with your shoes. You can't just leave your shoes sitting outside, because the moisture in them freezes. And his boots froze into the hardest blocks you could imagine. That big guy had his tiptoes in his shoes, and he was jumping up and down on the ice, and they weren't even bending. Not even bending. Finally, after about an hour of him cuddling with his boots, we had to cut them. I took my knife and I cut all the way down the back and down the front and spread it open as much as I could for him to jam his foot in there, and we tied it back up. I mean, he wasn't going to walk miles with no boots on, and like in the freezing cold, but that's how cold it was, right? So anyway, we got back all right. Obviously, I'm still here, right? No wolf's going to stop me. Okay, guys, so go ahead and submit that assignment, and we're going to move on.